In this lecture, what we're going to do is we're going to take a look at coming up with a relationship for the friction factor. And so if you recall at the end of the last lecture, we came up with the Darcy-Weisbach equation, which was an equation that enables us to quantify the pressure drop within pipe flow. And within the Darcy-Weisbach equation was this friction factor term here. And what we're going to be doing in the next few segments, we're going to look at it for both laminar as well as turbulent flow. And we want to be able to find a way to be able to quantify what this friction factor is. And once we are equipped with it, we can calculate pressure drop in pipes, we can do sizing problems, flow rate, diameters, a lot of different engineering applications, provided that we can come up with a relationship for the friction factor F. So what we're going to do, we're going to start with the governing equations. The equation that we'll begin with is continuity. And we'll express continuity in polar coordinates or cylindrical coordinates, which would be adapted to a pipe system. Now, in fully developed pipe flow, we know that there will be no swirl. The swirl would be velocity in the azimuthal or circumferential direction. Nor is there variation in this direction. Consequently, we can write v theta equals partial theta equals 0. So any term involving partial theta or v theta would be 0. And with that, looking at continuity, this term disappears. And we are dealing with fully developed flow, where we're saying that the velocity is not changing as a function of axial position, and consequently that term drops as well. And we have fully developed flow. And for fully developed flow, the characteristic we said was that the velocity was a function of radial location alone. It does not change with axial position. And so with that, continuity reduces to something quite simple. So if we integrate that equation, we get r VR is equal to the constant of integration. In order to determine what that constant of integration is, let's apply the boundary conditions. So one boundary condition would be at r equals capital R, which is the outer wall. Remember, what we're dealing with here is a boundary condition. If this is our pipe and this is radial location, it is from the center line. So R equals capital R would be the outer wall. And at that point, we know that the velocity in the radial direction, that would be the no-flow boundary condition, is equal to 0. And with that, if VR at the wall is equal to 0, and we have this result here, that tells us that that constant is 0, and therefore VR equals 0 everywhere in the flow. So that reinforces the notion that U is equal to U of R only. So that's what continuity tells us. Now let's move on to the momentum equation, and we'll be looking at the x component of momentum. So this is the momentum equation then, and what we're going to do, we're going to take a look at the different terms here. To begin with, we're dealing with steady flow, so that term disappears. We said there is no v theta or derivatives with respect to theta, and consequently those disappear. We said the radial velocity was 0 everywhere, so this term has radial in it, that disappears. And we said that the velocity does not change in the x direction, that we have fully developed flow. So that term disappears and that term disappears. So all of a sudden continuity reduces to a fairly simple equation. And what I'm going to do, let me just do a little bit of an expansion with this term here before we rewrite it. I'm going to pull the viscosity inside of the derivative. So what I'm going to do is rewrite this as 1 over r partial r, and I'm going to pull viscosity because viscosity is a constant. We can do this, and we'll have r mu du by dr. And the reason why we're doing this is because mu du by dr, that is tau. And so what we will do is rewrite this equation as 1 over r partial by partial r, and then we will have r tau. And the reason why we're doing that is because tau will be something that we're after in order to get the friction factor, tau being the shear stress. And so that's the logic behind making that substitution or that rearrangement. So let's carry on and rewrite what we have for the momentum equation. So we have 0 so we get that. Another substitution we can make, gx is equal to g sine phi. Now what was phi? Remember last lecture we had our pipe and we had the center line orientation here. Phi was the angle that the pipe made with respect to the horizontal. And we also had a coordinate system drawn. We had a z1 and we had z2. And then x was in that direction. And we're going to make a little bit of a flip here with sign convention. I'll get to it in a moment, but it relates to how x and z relates. And so what we can do, I will rewrite this now with the substitution. And we have an equation, 1 over r and pressure is only changing as a function of x. It doesn't change as a function of radial location. At a given x location, pressure will be constant across that cross-section area. So I change that to a total derivative. And then what I've done, I made another little bit of a trick here. I put this x in because we are putting the rho g x sine phi inside of the derivative operator, and that's why I've added an x there. So if that's a little confusing, that's the mathematical trick behind that. And the next thing we're going to do, we're going to make a sign change here. And the way that we're going to be able to justify that is as z decreases, x increases, or counter as x increases, z decreases. And consequently, I'm going to be able to change the sign here, and I can write this or rewrite it as d dx p plus rho g z. So I've now used the x sine phi in order to get and replace that with a z, and I flipped the sign because of this relationship here. So what we've now done, we've rewritten our equation. So we have that. Let's go to the next slide, and we'll put that up at the top because we're going to work with that. Now, this here, it varies with respect to r only, and this here varies with respect to x or z only. And we can use a bit of a mathematical formulation. And we did this when we were working with streamlines, stream functions, and potential flow. But let me write that out again. Okay, so the mathematical aside here, if we have two functions, we have f of x and g of x, and if we're taking the derivative of those, that should be g of y. So we have f of x and g of y, and we're taking the derivative. That gives us some function f of x and g of y. These functions are equal if and only if they are the same constant. And so you can look back here as basically that is what we have. We have something that is a derivative with respect to r and something a derivative with respect to x. And consequently, as we integrate either the left or the right hand side, it's going to be a constant, and that constant has to be equal. So let's take a look at applying this mathematical aside to what we have for within the pipe. So if we integrate the left-hand side of the equation, and then we know at the boundary condition tau is equal to 0 at the center line of the pipe, and that tells us that C1 is equal to 0, what we're left with is tau is equal to r times some constant, and that would be equal to RC. So we're going to take this now back up into this equation here. And I'm going to evaluate the left-hand side. So we get that for the left-hand side, 2 tau over r, substituting that back in. And we can solve for tau then. Okay, so that's a lot of work to come up with a relationship for tau and pipe flow. That's a shear stress. But what we're going to do in the next segment, we're going to take that and apply it to laminar flow, and that will be the method by which we come up with an expression for the friction factor in laminar flow. Once we get to turbulent, we won't be able to use this relationship, and we have to use other relationships for turbulent, but we're on our way to figuring out what the friction factor is for laminar flow.